Hi.
What topics are we going to cover today?
Today we are going to continue discussing sound waves, and in particular it will be introduction of sound level, which is measured in decibels. Then we will discuss Doppler effect and supersonic cases like Mach cone and shock wave. We will consider some case for which involves supersonic motion, like in the sound wave generated by an object with supersonic speed in air.
Good afternoon, Professor.
Hello, guys. Yeah, nice to see you. So these are main three topics we are going to cover, and this will be the end of mechanics for our course. Next week we start our discussions on molecular physics and thermodynamics. Okay. I believe we have already most of people who are going to join us. If not, someone can join on the way. And let me change the screen. Oops, that's not good. Let's check what's going on. Okay. Oh, this is better. So yeah, so today we start with the introduction of sound level, and we need to highlight that human ears are quite sensitive instruments, and we can hear very low intensity sounds. So the so-called threshold of hearing, which is defined at 1000 hertz, 1 kilohertz, is defined as I0 equal to 10 to minus 12 watt per square meter. So it's very low light intensity. And at the same time, we can hear like extremely loud sound, which is at this already at some painful level, which would be something about 1 watt per square meter. So you see it's like 12 orders of magnitude difference. And in order to make it more comfortable to quantify the intensity of sound, in this wide range was proposed to introduce such parameter as sound level and beta, which is equal to 10 times decimal logarithm of the ratio between sound intensity, for which we want to calculate the sound level, to this threshold hearing sound intensity at 1000 hertz. So this is the equation. This sound level is measured in decibels. So units are decibels. And let us maybe consider just some examples how it's calculated. So let's consider first sound intensity, which is equal to I naught, so 10 to minus 12 watt per square meter. So in this case, beta is equal 10 to minus 12 divided by 10 to minus 12. So actually this is going to be unity, and natural log of, not natural, decimal log of unity will be 0. So this log will be equal to 0. 0 times 10 equals 0. So 0 decibels is sound at the, let's call it, edge of hearing. So it's the threshold of hearing when we barely can identify the sound. That is considered to be set as 0 decibel. So if, for instance, we have intensity of sound equal to, let's consider this 1 watt per square meter, then we will get, for this case, sound level will be 1 divided by 10 minus 12, which is 10 to 12, and decimal log of 10 to 12 will be equal to 12. So if we have a product of 12 to 10, will be 120 decibels. And this is the sound level, which is already painful for humans. It's kind of upper level where you can distinguish sound as a sound, not just some shock wave which hits you. So here I would like to focus your attention on one interesting thing as sensitivity, like let's say spectral sensitivity of human ears. So as I mentioned, this parameter I naught is defined at certain frequency at 1 kilohertz. It's maybe you already noticed this from your everyday life experience, but our ears, they have different sensitivity in different frequency ranges. Moreover, it also depends on the level, sound level, like sound intensity. So it's really not linear dependence. It just depends on both frequency and sound level. So if we plot such system of coordinates where will be frequency in logarithm scale. So let's say we start from 20. So by the way, do you know the frequency range in which we can hear sounds?
From 20 to 20,000 hertz.
Yeah, something around this. It can change from person to person. Specifically, when we get older, we lose capabilities to hear high frequency, but under normal conditions, this is the range about 20 to 20,000 hertz. Will be 1,000, and somewhere here, let's put 20,000 hertz. So this is logarithmical scale. And here, let's put this sound level, which like maximum value, we consider 120 decibels. So there is such a frequency, and maybe to make it a bit more convenient, I push this 1,000 to the right. And now, something like this. And here. So what does it mean? So this area defines conditions, how we hear, how we perceive the sound. So why 1,000 hertz is kind of important in acoustics in the field of studies which deal with sounds. So we have the best hearing of this frequency, what means if sound level is very high, let's say 120 decibels, then we don't have any frequency dependence. We kind of go to saturation. Our detector, like ears, go to saturation regime, and we hear at any frequency extremely loud sound equally. It's just painful feeling, that's all. But when sound intensity drops, then we have different sensitivity to different frequencies. So beyond this area, which is dashed, we don't hear anything. What does it mean? So if, for example, there is some sound wave with frequency 20 hertz, and its level is, let's say, 50 decibels. It's just rough number in this scale, just to show you. You see that if we cross this at this point, it will be outside this dashed area. Means that the intensity, like sound level of this frequency, will not be enough for our ears to detect it. So in order to hear this sound, we need to increase this intensity, sound level up to, I don't know, let's say 70 decibels. Then at this frequency, we will start hearing it. But at the same time, if we consider 1,000 kilohertz, like 1,000 hertz, at 50 decibels, we will clearly hear it because our ear as a detector of sound is much more sensitive for this frequency range. That's why we can hear the lowest sound level possible at 1000 hertz. That's why the hearing threshold is determined at this frequency. At 1000 hertz, we can hear sound intensity of amazingly small value, which is 10 to minus 12 watts per square meter. And this is not some unique feature of our ears as a detector of any signal. Every detector, for instance, our eyes or some photodiodes, they also have spectral distribution of their sensitivity. And this should be taken into account because there is, for instance, if we consider our eyes, so that will be more probably from optics course. But if we consider our eyes, there is such photopic spectra, which shows how sensitive our eyes are to different wavelengths. And then when you can plot a product of light spectrum and photopic spectrum, you will see the real response of our eye and what level of signal we will detect. So that should be taken into account, that ears and eyes and other even artificial, some devices, detectors of any signals, they possess different spectral dependencies, and also their response can depend on the intensity of the signal. So ideally, when it's linear dependence, so it's called, maybe you heard in this, for instance, in cameras or like smartphone cameras or photo cameras, there is such parameter as linear dynamic range. So it gives you how many orders. It also actually measured in decibels because it tells you in how many orders of magnitude you can change the intensity of your signal, and your response means the dependence of your detector response on the intensity of your signal will remain linear. So that is very important parameter because it will realistically show you the detected signal. It will not have some nonlinear dependence when it will become too bright or too dark. So that's why you want to have a detector with as wide linear dynamic range as possible. Okay, so that's enough for sound level and decibels. And let's go to Doppler effect. So I guess you also notice this at some conditions that, for instance, if we have a moving source of sound, let's say some car or train, and we have a not moving observer. So this moving source of sound can move in two directions. It can move towards the stationary observer or away from stationary observer. And with some speed of, let's call it V naught. So we have some source of sound. And if it doesn't move, it stays on the same position, we have some characteristics of this sound, which is the frequency, wavelengths, lambda, and speed of sound in the environment. In our case, let's say in air. So if this source of sound starts to move, for instance, it moves towards the observer, so it moves to the right, the characteristics of the sound which observer hears will differ from the real characteristic of this sound when the source was not moving. This happens because we kind of sum up the speed of spreading of sound wave to the speed of moving this platform. And that's why we end up with higher speed of sound approaching the observer. And that results in changing the characteristics of the sound we detect. It actually, if we increase the speed, we decrease the frequency, and we hear higher frequency than it is indeed without moving of the platform. So let us consider this case. We have like frequency is defined as the ratio of speed of sound divided by wavelengths. And if this source of sound is moving towards the observer, then we end up with some apparent frequency which observer can hear, which is frequency prime, is equal to speed of sound plus speed of the sound source will be V naught divided by lambda. So from other side, lambda can be expressed as speed of sound divided by frequency. So we put here, instead of lambda, speed of sound divided by frequency will be V plus V naught divided by V, and everything is multiplied by frequency. So we see that instead of hearing real frequency of the sound generated, which is F, we hear some apparent frequency F prime. And since V naught is positive because under given condition, it approaches the observer, so we can sum up the speed of sound and speed of the sound source. We always have this ratio larger than unity. So that's why F prime is always larger than F. And as a result, we hear this sound as it is with higher frequency than it is generated indeed. So if, for example, now we consider the other case when the source is moving away from the observer, then we need to subtract this velocity from the speed of sound. That's why our frequency, let's say double prime, when the source is moving away, will be equal to speed of sound minus speed of going away platform or sound source divided by speed of sound times original frequency of the sound. And we see here that under these conditions, this frequency double prime will be always smaller than the original frequency. So we will hear it at lower frequency than it is indeed. Okay. So this is one case. Need to consider another possibility. Let's say what will be if we have a stationary sound source, but the observer is moving, either approaching the source or moving away. Oh, okay. Yeah, I messed it up a bit. So everything what I told you is for the moving observer. So we have V naught minus V naught and stationary sound source. So when we approach the sound source, like when the observer is approaching the sound source, we sum up these velocities because we have speed of sound, then we have speed of observer, and we end up with higher frequency. If we're moving away from the sound source, we subtract and frequency will be low. So now in the contrary, we consider another case when the source is moving from the observer or approaching observer. So like this.
Excuse me, Professor. Can I ask
Yeah.
one question?
Sure.
So when in the double F case, when a person is moving away, you said that F double prime will be always less than frequency, but V speed of sound, yeah?
Yeah.
And can we consider that speed of sound is always larger than V0, and that's why like this subtraction will only give the
Yeah. It's a good point. So in this case, we do consider this, that we don't move faster than the speed of sound. Otherwise, we will literally not hear it. We will kind of run away from the sound wave. And let's say that we will, at the end of this discussion, spend some time discussing this supersonic case. But in this case, yeah, if you move with V naught larger than V, then means sound wave cannot reach you. So you just run away from it.
Okay, thank you.
Yeah, so this is some boundary condition which you cannot just consider. You cannot apply this to calculate frequency of what you hear because you will literally hear nothing. So now let us consider the case when the source of sound moving. Sorry about that, I messed it up. It's kind of all similar, but with some minor differences. Eventually, we will get the final equation, which takes into account both conditions. So you can then see what is given for a specific problem and apply that equation to describe quantitatively your case. So if, for example, source is approaching observer, then we have some lambda prime. It's approached from a bit different direction to this question. So we can consider also change in wavelengths, not only change in frequency. So lambda prime will be lambda, which is the wavelength of the sound which is generated, and then minus some delta lambda. So we will reduce wavelengths of the sound which we hear with respect to the sound which is wavelength of the sound which is generated. And this delta lambda can be expressed as so lambda minus Vs, which is speed of the source, divided by frequency of the sound. So now we can write that frequency prime, which we hear, will be speed of sound. Speed of sound doesn't change. Divide by lambda prime. And instead of this lambda prime, we put in the denominator this expression for lambda prime. It will be V divided by lambda minus Vs divided by F. So now we can get like this, rewrite it. It will be lambda times frequency minus Vs divided by frequency. So lambda times frequency is nothing else as speed of sound. So we end up with speed of sound divided by the difference between speed of sound and speed of the source, and this times frequency of the generated sound. So in this case, we see that if speed of sound is, if the source of sound approaches the observer, then we have minus here in denominator, and that's this ratio is always larger than unity. And that's why, again, we get the condition when frequency prime is larger than frequency. So we will hear sound with higher frequency. So if the source of the sound is going away from observer, we will need to change the sign in the denominator. It will be F double prime equal to V divided by V plus V so S times frequency. So this ratio will be always smaller than unity, and that's why F double prime will be smaller than frequency of the sound. Okay, now we can consider simultaneously both moving source and observer, and let us just for as an example consider when they approaching each other. So both source and observer are moving towards each other. Then there will be some frequency F prime, which observer can hear, and this will be taking into account equations which we derive for both cases. It will be V plus V naught, which is speed of sound plus speed of the observer, then V minus Vs in the denominator will be speed of sound minus speed of the source of sound. n times original frequency. So in this case, obviously, f prime will be smaller than frequency. And if indeed this is, if we write in general case, we can write plus minus, because it really will depend either objects are moving towards each other or objects are moving away from each other, or let's say source of sound approaching the observer and observer is moving away from the source of sound. So there are different combinations and they will correspond to different signs, either plus or minus in denominator and nominator. But in general, this equation can give you the describe this Doppler effect, taking into account both sound source and sound receiver, like observer, moving in different directions with respect to each other. By the way, need to again highlight more general picture of this. It's not applicable only to the sound. It is also true for example, for electromagnetic waves. Maybe you heard about such term in astronomy, astrophysics, as redshift of stars or galaxies. We know that some certain chemical elements, when they are excited, they emit light of certain frequency. It's defined by the nature of this matter, of this material, atoms. So they should be the same, doesn't matter where they are. However, what is observed from far galaxies, that all these peaks, which should be at certain wavelengths, they are shifted to longer wavelengths. And this is called redshift. And this redshift is, they figure out that this redshift depends, it's not constant, it's increasing, it increases as the distance from Earth to these objects increases. Means that our universe expanding, and the further objects are located from us, they move with higher speed, like moving away from us as an observer, and that results in this Doppler effect, redshift for electromagnetic waves of the emission originated from some excited atoms in excited material in these galaxies. So this is like broader picture of Doppler effect, which is applicable to different kinds of waves, not only sound waves. But sound waves is most common what we really can observe in our everyday life. So now let's proceed to the supersonic case. That's also something what we can observe in our life, but not usually everyday life. We usually don't observe objects which are moving with speeds which are higher than speed of sound. The speed of sound in air is quite high speed of sound. It's like kind of high speed. And usually all objects, including all commercial airliners, they all move with speed which is lower than speed of sound. However, there are many cases when speed exceeds speed of sound, and this is what we want to consider now. So maybe I move to another slide. And now it's usually given in textbooks. This we will call now, like discuss now the cone of like Mach cone, so-called, which is the shape formed by shock wave, which results from the interference between wave fronts of different sound waves which interact, which were generated by such object which moves with supersonic speed. And because of this interference effect with this shock sound wave forms, we end up with a shock wave. So in order to make it clear, I'm sure you have seen this many times, but usually in textbooks, you see already finished picture with these circles, which are reducing in radius, and then some tangential lines, which define the cross section of this Mach cone. But in order to really understand this and remember, it's important to draw it once, step by step. And that's what we are hopefully can do now, but it will not be very accurate, but we will try to do it. So let us consider the case when we have speed of some plane let's call it Vs, like will be speed of source of sound, are equal to two times larger than speed of sound. So in this case, let us have some axis here. And let's consider some time interval of 5 seconds. So here will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in 5 seconds, distance between these points here is the distance which sound can move through in 1 second. So since our source, our plane, is moving with twice higher speed than speed of sound, in 5 seconds it will move along 10 distances of this. So it will be here. And here it will be at second 0, here second 1, here second 2, here second 3, here second 4, and here is second 5. Okay, now let us draw a sound like waveform of the sound which was generated by this plane at 0 time. So since that moment when it was generated and our plane moved from this point to this point, like to the end, point number 5, we had in total 5 seconds. So that's why our sound could travel distance which is equal to this 5 distances. So let us put them here. Let's put axis y for reference and try to put equal 5 distances. 1, 2, 3, 4, 5, somewhere here. So means that in the cross section, the spherical waveform will be a circle with radius of 5 distances. So it will be 5 here. So we can draw very roughly a circle. Will be also 1, 2, 3, 4, 5 here. Something like this. So let us then consider what will be the waveform which was generated in point 1, like in time equal 1 second. So from point 5 to point 1, we have 4 seconds. That's why we will have a radius of 4 distances. Will be 1, 2, 3, 4. So it will go here, and we will count 4 from here to the right. 1, 2, 3, 4. So it will go here. We will have some 1, 2, 3, 4 here. Okay. One, 2, 3, 4. This circle. Okay, now we go to point number 2. So let's consider what will be the waveform. We have 3 seconds difference between point 2 and point 5. So the radius should be 3. So it will be 1, 2, 3 here, then 1, 2, 3 here, 1, 2, 3 here. So it will be something like this. Then point 3, difference is 2 seconds with 0.5. So we need to put here 1, 2, here 1, 2 also. So it will be like this. And finally, let's consider point 4 will be difference in 1 second, and our waveform of the sound will be just radius of 1 interval. Will be like this. So here in point 5, our plane just arrived. That's why it just generated sound. It didn't have time to travel anywhere. So this picture looks terrible, I know, but even with such terrible accuracy, you see that we can have some common tangential to all these circles, most of them. And this is the cross section of the Mach cone. Here, half of this angle, alpha, is called Mach angle. And now let us figure out what will be the this angle. So in order to do this, we need to consider first circle, which takes into account the first the waveform which is generated at point 0. Then put a perpendicular, so radius, which will be right angle to this tangential line. So here we will have right angle. So we have right angle triangular, and this hypotenuse, like this longest side of the triangular, we know this length because this is our time interval times speed of our source of sound, our plane. So let's call it A, B, and this point C. So A, B is equal time interval times speed of the source. Then this distance we also know, AC. AC is the radius of our waveform, and this will be the time interval times V, which is speed of sound. That's why this angle, actually here is also alpha. This angle alpha, so the ratio between AC divided by AB will be sinus alpha, and taking into account this, it will be V divided by Vs. So the Mach, the angle of this Mach cone will be defined by this equation. Sinus alpha is equal to the ratio between speed of sound to the speed of the source, like moving object. And this can be written as sinus alpha equal to 1 divided by capital M. So capital M is equal, it's called Mach number, and is defined as the ratio between speed of the source to the speed of the sound. So it actually tells us in how many times speed of the plane or other object moving in the medium is higher than the speed of sound in this medium. That's why sometimes, like very often, some supersonic speed is measured not in meters per second. It just said like 2 or 3 Mach. Means that it exceeds speed of sound in like 2 or 3 times. In our particular case, which we considered here, this cone, Mach cone, which we have drawn, is the Mach number equal to 2, because our speed of the source is twice higher than speed of sound. So we are running out of time. I believe this is everything what I like critically important what I wanted to tell you, and you can ask questions if you have any questions. But I believe that I really wanted to draw this step by step to show you how you get to this point, because I believe this is quite memorable, and you just understand how this shock wave actually, by the way, this edge of the Mach cone is called shock wave. So it's if observer is here, then you don't hear anything, because you will not hear anything until this tangential of the Mach cone will reach to this point. And then you hear shock wave, which is kind of an explosion. It's a very abrupt change in pressure at the edge of Mach cone. Okay, guys, thank you very much for attention. I congratulate you that we did it and managed to finish mechanics part of our course. So have a good weekend, and on Monday we will start discussing already molecular and physics and thermodynamics.
Okay, thank you very much, Professor. Goodbye.
You are welcome. Okay, have a good evening. Bye-bye.